Hi, everybody. This is Calculus 2, Section 9.6, the ratio and the root test. Ratio just means fraction. So what in the ratio test, what we're going to do is divide by divide. We'll have a numerator and a denominator, and we'll divide. So it'd actually be a fraction divided by another fraction. And the root test is exactly what it means, taking the radical of a function. All right, so let's take a look. Once again, we're going to be doing the ratio test, the root test, and then reviewing everything we've done up to this point. The ratio test. So here's our series A sub n. The ratio test, once again, is a fraction. What we do is find A sub n is in the denominator, and the next in the series would be A sub n plus 1. We put the next number in the series on top. And if the fraction is less than 1, we say it converges. If the fraction is greater than 1, we say it diverges. And if the fraction equals 1, it's inconclusive. We can't determine whether it converges or diverges using this method. All right, let's take a look at an example. Here we go. 2 sub n over n factorial. If we look, and so that's our A sub n. If we look at A sub n plus 1, if we put n plus 1 in here instead of n, we get 2 times n plus 1. And if we put n sub 1 in here, n plus 1 in there, we get 2 plus 1 factorial. So once again, we said we're going to divide this. So we take this and divide it by, actually, if you remember, the A sub 1 goes on top. So that means it's the A sub n plus 1 on top. And then divide it. You can do it like this. This is the A sub n plus 1 on top. And the bottom would just be the 2n over n factorial. Another way to look at this is 2n plus 1 over n plus 1 factorial, divided by this. I guess I'll go out and do everything. And then you can rewrite it. And when you divide fractions, you change the multiply and flip the second fraction. This fraction gets flipped. So this is where we're at. I'm going to go ahead and erase everything else just to show you. I mean, that's a lot of work to get here, but you really don't have to do that. You can just next time do this and then multiply it by the reciprocal of this. And that's what we did here. All right, so let's erase this stuff. And I'm going to rewrite this. This becomes, if I distribute, 2n plus 2. And if you know n factorials, n time, then you always subtract 1. Then n plus 1 factorial is n plus 1 times, subtract 1 from it, then you get n times n minus 1 times n minus 2, and so on and so on. Another way of writing this would be n plus 1 times n factorial. Because this is the same thing as n minus 1, n minus 2, and so on and so on. Multiplied all together. Then we're going to multiply this by n factorial over 2n. And if you look, n factorials cancel, 2 to the n's cancel, and we're left with 2 over n plus 1. So if I take the limit, as n approaches infinity to 2 over n plus 1, I end up with 2 over infinity plus 1, which is 0. So this is, this ratio is equals 0. That is less than 1. So the series converges. All right, so let's see what they did. And they did the same thing I did. Canceled out. They put infinity into the n equals 0. It's less than 1. So the series converges. A sub n plus 1 on top divided by a sub n. All right, next is the root test. If you have a series a sub n and you take the radical, but the root is going to be n, so the n could be 1, the root could be 1, could be 2, 3, 4 as we move on. If the root of a sub n is less than 1, the series converges. If the root of a sub n is greater than 1, it diverges. And once again, if it equals 1, it's inconclusive. So here's a sub n. If I take the whole thing in radical form, I get this. You can also do, if you wanted to, you can also do this. That's an n. You can break it apart. You can break it apart if you want. And if you notice, the power and the root can cancel. Here, same thing. The root and the power can cancel. It still has an e to the 2, but it can cancel like that. Now, if you take the limit as n approaches infinity, and put infinity down here in n. This is a constant. So it's just a constant divided by infinity, which equals 0. And once again, 0 is less than 1. So using the root test, this converges. That's really not too bad. I mean, we have some really nice, easy examples here. And we'll try a couple of homework problems also. Okay, so let's look at the rest of the slides. These are the different things we've gone over in chapter 9. Guidelines for testing a series for convergence or divergence. Does the nth term approach 0? If not, it diverges. So when we're looking at a series, the nth term should approach 0 if it's converging. Is the series one of those special types? And we've looked at these: geometric, p-series, telescoping, or alternating, and the different ways they converge or diverge. Then we looked at integral just now. Not now. We didn't look last time, I think, in one of the previous sections. The integral test. We've looked at the root test and the ratio test. And then we also looked at the comparison test. So we've done all of this already. And it's really, I would keep this nearby and say, hey, look, these are all the possible things I can do. So let's look at A first. First thing I recognize, I see a 1/3 there, but let's go to the next slide. For this series, the limit of nth term is not 0, it's 1/3. So since it doesn't approach 0, it diverges. Here is B. This looks looks a little wrong. I don't know if it was the fonts or what, but it doesn't look like it's in order. I don't know how that happened like this. The series is geometric, moreover, because the ratio of the terms r equals pi/6 is less than 1 in absolute value. You can conclude that the series converges. R, don't forget pi is 3.14. 3.14 divided by 6 is less than 1. So I just want to go back and show you this. This is r to the n. There's a geometric, and if r is less than 1, then the series converges. And this is r, pi is 3.14. This is less than 1. C. C, don't forget that sometimes it's easier to just integrate something. This is x e to the u, where u equals negative x squared, and the derivative of u is negative 2x. So in here, I can put a negative 2 on the outside of this function when I integrate this. If I put a negative 2 there, I have to put a negative 1/2 here, because it has to cancel out and look like this. And now it does. So this is the du part. So derivative of e to the u is e to the u du. So we end up with negative 1/2 e to the u is a negative x squared. Du is a negative 2x. And we see all this cancels out. So we should have got that. If you see right back up there at the top. And I want to go back up to D. This kind of looks like, if you look at this, looks like you can do a comparison test possibly. And they did say after using the limit comparison test, it's a harmonic series. And remember, harmonic is when P equals 1. P equals, when you do a harmonic series and P equals 1, the series diverges. We still have E and F. E definitely alternating. It's an alternating series. And it says this alternating series converges. Make sure you look up alternating series and see why it converges. F. You should have all these written down right in front of you. F is one we just did we used the ratio test. Right, the top would be n plus 1 factorial, the bottom would be 10 to the n plus 1. This divided by this. And you can take a look at that. Just the way we just did it just 5 minutes ago. And here it says it diverges. So take a look at that. Obviously, the ratio is equal, greater than 1. Maybe we should do that since it is greater than 1. Let's take a look at that. So let's look at F. So we're going to do n plus 1 factorial over 10n plus 1. Divided by, but I'm going to multiply it and flip it, 10 to the n over n factorial. So this becomes n times, and this becomes n plus 1 times n factorial over 10 to the n plus 10 times 10 to the n over n factorial. N factorials cancel, 10 to the n's cancel, and I'm left with n plus 1 over 10. Put in and take the limit as n approaches infinity. The top is larger than the bottom. So this is greater than 1. Because the top number is larger than the bottom, this becomes greater than 1, so it diverges. So here it says you can use the root test, the nth term. So since we have the nth term of series involves a variable, that's a good indication of whether you can use the root test or not. If we go back up here to the example we had on the root test, you see how we have an n as a power of each one. And so this can be written as n plus 1 to the n over 2n plus 1 to the n. So if we do the root test, we can or we could have just did this. Doesn't matter. It cancels out there, or each one cancels out here. And we're still left with n plus 1 over 2n plus 1. These cancel out, and you just left with 1/2, which is less than 1. So the series converges. And that is the end of this section. So if you see, there's a lot involved here. There's a lot of different things involved. Look at all this. This is a really good 2 pages of notes here. And if you want to print out these 2 pages of notes, I'm going to allow it for this test because this is a lot of good information that we need to have. This, like I said, this is really good. So I will let you use these 2 pages of notes. All right, well, I hope that helped for this section. Just the ratio and the root tests aren't too bad. It's all the other stuff when you combine it all at once, determine which test you're going to use. That's a little bit more complicated. So I really like this summary of tests for series. So let's print this out and use this also in our notes. You guys have a good day.